All right, let's look at a few of the homework problems from section 1044, just so we can all make sure we yeah, we can go ahead and make problems. So look at number 10. This one's asking us to find the equilibria and then to find the linearization, which is always kind of the, I don't want to say challenging, but no, it's challenging. This is challenging for me. So here's our system of non-linear differential equations. dx1 dt is x1 minus 2x1 squared minus 6x1 x2, and dx2 dt is 2x2 minus 8x2 squared minus 2x1 x2. Welcome. It's always, gosh, especially in the book, like seeing like the x sub 2 squared, the x sub 1 squared, it looks just like really kind of messy in it. But so we have, so to find equilibria, thank you, we're going to be setting these both equal to 0 and trying to find the simultaneous solutions. If we were going to graph these, if we were going to graph the null lines, which we probably won't, but if we were going to graph them, it would be where the different types of null lines intersect with each other. So let's see what we can do. So looking at either one of these, I'm trying to see where this is equal to 0. I'm going to try and factor as much as I can. This is a kind of, it's a fairly standard-ish way of like writing an equation. Oftentimes you'll see nonlinear differential equations like this where you have each term having like an x1 or an x2 in it. So we can factor out an x1 here, and we're left with 1 minus 2x1 minus 6x2 equal to 0. Similarly here, if we set the second one equal to 0, we're going to get an x2 factored out. We're going to have a 2x2, sorry, not a 2x2, a 2 minus 8x2 minus 2x1. And then we're going to try and find solutions where both of these are equal to 0 at the same time. So as is often the case, what's one of the solutions?
0.
Right, not just 0 though, but 0, 0. So one solution, one equilibrium is x1 hat, x2 hat equal to 0, 0. But then, right, you want this product to be 0. So you could have x1 being 0, or you could have this other factor being 0. So then we can say, we could also have the case where x2 is 0 and this other factor, 1 minus 2x1 minus 6x2 equals 0. But then since we know x2 is equal to 0, this term is gone. So then we're going to have 1 minus 2x1 equal to 0, which is going to give us x1 equal to positive 1/2. So another equilibrium is x1 is 1/2, x2 is 0. I'm going to give you all a moment to find the next one. So the next one, do the opposite thing. You're going to say, well, we could have x1 being 0 in this one, and then instead of x2 being 0, we could have this other factor being 0. So I want you to try that one. x1 equal to 0, and the other factor, 2 minus 8x2 minus 2x1 equal to 0. I'll give you a minute. Did I hear something survey? Okay, I'm sorry. Sometimes I don't remember all the things. And the attendance form is over there too if you need it. Okay, so let's see. If I plug in x1 equal to 0, I just have 2 minus 8x2 equal to 0. So I'm going to get x2 equal to 2 divided by 8, which is 1/4. So we also have 0, 1/4. And then lastly, we have the possibility of this being 0 and this being 0 at the same time. And that's usually the most complicated one. Basically, right, if we think about the null, I think, yeah, you know what, it is worth graphing the null lines. So just for a second here, not that you're asked to graph the null lines for this problem, but if you think about graphing the null lines, so I'm drawing different colors. So x1 equal to 0. And again, if this is the x1 axis, and this is the x2 axis. Here is the line x1 equal to 0. That's one of my null lines. Here's the line x2 equal to 0. And then these lines are also terrible to draw, but they look, right, if I solve this one for my quote unquote y, right, thinking of x2 as y, this is looking like 6x2 equal to 1 minus 2x1. So x2 equals 1/6 minus 1/3 x1. I can kind of graph that, right? Let's see. If x2 equals 1/6 minus 1/3 x1, I have a y-intercept of 1/6, an x-intercept of 1/2. It's going to look something kind of crazy, maybe like x-intercept of 1/2. There's my y-intercept. My y-intercept of 1/2. Sorry, my y-intercept of 1/6. Apologies, and my x-intercept of 1/2. And then you'd also have a line from this one here, which would also be kind of bonkers. It'd probably look something, I don't know, probably something like that. And so then, I wish the colors showed up better on this. You guys totally can't see I'm using different colors, can you? That's a bummer. Can I make it brighter? Can you see it? Nope, sure can't. Oh well, that's not helpful at all then. Sorry, the colors don't show up so well. I think they would. So basically, we're finding all these points. This point here, 0, 1/4. This one here, 1/2, 0. This one here, the origin, and this one here, which we're about to find, where those two lines intersect. So those are right where different null lines cross. That's where we get equilibria. Again, not what this question is asking you to do, but it's good to make that connection because you're definitely going to be doing that in section 7.6. Right, the next homework assignment definitely has problems where you're doing graphing the null lines and graphing all the arrows in the thing. So if I had to figure out which one was which, I would, well, I guess I've already taken this one and solved for x2. So I'm going to plug that into the other equation. So I have x2 equal to 1/6 minus 1/3 x1. I feel like I should double check that work. Yeah, that looks all right. This equals, yep. Okay, and then I'm going to plug that into this equation here. So 2 minus 8 times x2 minus 2x1 equals 0, which seems kind of awful, but we can make it better. I would multiply everything by 3. So multiply by 3. I'm going to get 6 minus 24 times 1/6 minus 1/3 x1 minus 6x1 equal to 0. And then 24 times 1/6 is 4, and 24 times 1/3 is 8. So then I have a 2x1, I should say I have a 2 plus 2x1 equal to 0. So I get an x1 equal to -1. And then if x1 is -1, x2 is going to be 1/6 plus 1/3. 3/6 plus 2/6 is, 1/6 plus 2/6 is 3/6, which is 1/2. So my last one is x1 is -1, y1 is, or x2 is 1/2. That one's a little messy. So there are 4 equilibria from this system, nonlinear differential equations. Again, you're just trying to find all the points where both equations are 0 at the same time. So 0, 0 works, and 1/2 for x here and 0 for y. Sorry, I keep saying x, y. 1/2 for x1 and 0 for x2 works here and here and so on. And if you plugged in these points, -1 for x1 and 1/2 for x2, you would get each of these parts equaling 0. So the whole thing, both systems would be 0 at the same time. The other part of this question is to find the linearizations at each of, it's a long question. We have to find the linearizations at each of these equilibria. So let's remind ourselves of the formula for the linearization. Is it really this whole thing? It really is. Yeah, you need two equations. It's so much fun. Okay, so here's the linearization. So okay, we'll do it this way. So we're going to call the first equation F1. And that's your x1 minus 2x1 squared minus 6x1 x2. And our second equation is F2, which is dx2 dt, which is 2x2 minus 8x2 squared minus 2x1 x2. And then there is so I feel like now would be a good time to talk about kind of the more compact way of writing this. So you can totally do it kind of the long way where you write each thing. Let's actually, before I even get there, let's find the partial derivatives. So we know that our df1 dx1 is going to be 1 minus 4x1 minus 6x2. df1 dx2, I guess I should be saying del, not d, is going to be minus 6x1. Our del f2, del x1 is going to be minus 2x2. And our del f2, del x2 is going to be 2 minus 16x2 minus 2x1. And so usually when we do this linearization, it's kind of this gross formula where we say, okay, yeah, it's a lot. So we say that the linearization of f1 at x1 hat x x1 x2. Sorry, this is where the hats always get kind of. So we should remind ourselves, x1 hat x2 hat is the equilibrium, whereas x1 and x2 are just the variables. So we're finding the linearization of x1 and x2 of this first thing, and it's going to be the following. It's going to be this function evaluated at your equilibrium. And then it's going to be each partial evaluated at your equilibrium times the difference between your variable and the equilibrium. So it's going to be the partial of f1 with respect to x1 at x1 hat x2 hat times x1 minus x1 hat plus the partial of f1 with respect to x2 x1 hat x2 hat times x2 minus x2 hat. And the same thing for L2, the linearization, except with f2s instead of f1s. So L2, the linearization of the second function at x1, x2 is f2 at x1 hat, x2 hat, plus f2 partial with respect to x1. I'm just copying down the same stuff, except using an F2 instead of an F1. Okay. So what I wanted to say about this is two things. First thing, every time you do this linearization, this part here is 0. Because you're plugging in the equilibrium point back to the differential equations. But the equilibrium is where the differential equations are equal to 0. Right, so if I plug back in, if I'm going to do it 0, 0, and I plug 0, 0 back into each of these equations, I'm going to get 0 for each of them, or any of the other equilibria. So that part's always 0. And then what I want to say is we can write this as a matrix. This L1, L2, I'm going to write as a vector. The vector for the linearization. And it's equal to the Jacobian matrix, right? It's my here, right? It's all my partials. F1 with respect to x1, F1 with respect to x2, F2 with respect to x1, F2 with respect to x2. That's just my Jacobian. All right, so it's del F1, del x1, del F1, del x2, del F2, del x1, del F2, del x2. It's my Jacobian times x1 minus x hat 1 hat x2 minus x2 hat. Which maybe is less terrible. The thing that's still kind of terrible about this, unfortunately, is you do have to do it for each point. Meaning we have to do it for 0, 0, and 1/4 0, or 1/2 0, and 0, 1/4, and whatever the fourth one is. Let's do it for one of them, and I'll leave the rest to you all. So let's say we want to find the linearization at, let's pick 1/2 0. So we want to find the linearization at the equilibrium x1 hat, x2 hat equal to 1/2 0. So what I'm going to do is I'm going to look back at my partial derivatives here so I don't have to do the work again. So plugging in my partial derivatives, I can find that my Jacobian is equal to the partial derivative with respect to that at x1 hat, x2 hat. So I'm going to plug in 1/2 0 there. I'm going to get 1 minus 2 minus 0. And I'm going to plug it in there, and I'm going to get -6 times 1/2. And I'm going to plug it in there, and I'm going to get 0. I'm going to plug it in there. I'm going to get 2 minus 16 times 1/2 is 8. So 2 minus 8 minus 0. So that ends up being -1, -3, 0, -6. So then here's what my linearization looks like. My linearization as a matrix multiplication looks like that matrix, -1, -3, 0, -6, times x1 minus 1/2, x2 minus 0. So this is a much more compact way of writing it. Now let me write it out the long way just so you can see it. If I want to write it out the long way, right, this is my L1 of x1, y1, L2 of x1. Sorry, x. I keep wanting to do y's instead of x's. x1, x2, L2 of x1, x2. So what we're really saying with this is the linearization of f1, which is L1, is -1 times x1 minus 1/2 minus 3 times x2 minus 0. And the linearization of the second function at this equilibrium 1/2 0 is, oh, sorry, I got a little carried away there. No, that's fine. No, I didn't. Just kidding. Is 0 times x1 minus 1/2 minus 6 times x2 minus 0. You could and probably should simplify these. This is going to be -x1 minus 3x2 plus 1/2. And this one's going to be minus 6x2. So when all is said and done with these linearizations, you should just be getting a constant times x1 plus a constant times x2 plus a constant. That's it. That's as complicated as a linearization can be. A multiple of x1 plus a multiple of x2 plus a constant, or whatever your variables are. So the linearization part is the part that I like the least. The rest of it's not so bad. The linearization just feels like a lot of writing. Questions about any of this? So, I mean, this is definitely one of your homework problems. You should obviously do the other parts of it, but you should do the other parts of it, right? It's a good problem to finish. Let's look at, I want to look at one of these actually. So let's, what time is it? Okay, I want to get some of the graphic stuff, but we should make sure we do this. Oh, yeah, sorry. Can you see this? So I thought it was actually, so I was reading the book because, you know, I wanted to. If you think about, so the book talks about the stability criteria for the Jacobian in terms of just the determinant and the trace. So basically, if the determinant's negative, unstable, right? Because you have a, what do you have if the determinant's negative? You have a saddle. And then they say also, sorry, I want to go back and look at it now. Yeah. But if the determinant's positive and the trace is negative, then it's stable. Yeah, definitely. So we know if the determinant of our matrix is negative, then it's unstable because we have a saddle, and saddles are unstable. Now, that's actually not what the book says, although it does say that, it just doesn't say it explicitly. Here's what theorem 16 actually says in the book. So they say part 1, or they actually say 2 things. So if these 2 things are true, if the determinant of J is positive and the trace of J, or Jacobian, is negative at your equilibrium, then the system is stable. At that equilibrium. And then they say the rest in kind of a less than easy way to read. Here's what they write after that. If the inequalities in either the first thing or the second thing or both are reversed, then the equilibrium is unstable. So here's what they're basically saying. If either, so this is the first thing they're saying, here's the second thing they're saying. If the determinant of J is negative, oh, that's what we said, or if the trace of J is positive, or both, then it's unstable. And the reason it's unstable is because those are the 3 situations that correlate to it being unstable. Because if the determinant's negative, we have a saddle. If the determinant's positive, then if the trace is positive, it means your eigenvalues are either real and positive or not real, but having a positive real part. So it's either an outward spiral or an unstable node. But basically, right, if you look back to this picture here, sorry, this is a good picture. Look back to this picture here in your book, the trace being positive is unstable all the time. Whether you're down here as a saddle or you're up here as an unstable node or an unstable spiral. So if you can see that the trace is positive, it's unstable. To be stable, you have to have the trace being negative and the determinant being positive. Both of these things have to be true for stability. Yeah.
Is this the one where you use the formula trace squared minus 4?
You don't have to. So what the book is getting at here is you actually don't have to use that formula, because that formula specifically is determining whether you have like a spiral versus a node, because you're trying to see if your eigenvalues are real versus complex. But what really is happening with a nonlinear system of differential equations is that the system is acting like that just near that equilibrium. But as you move away from it, it's really not acting like a spiral or node or whatever. So it's not really correct to say we have a spiral there. It's correct to say we have stability if it's an inward spiral, or instability if it's downward spiral. So we kind of just, you certainly could look at the eigenvalues the same sort of way we had before and determine stability that way. But this is another way the book's saying you don't really have to even do all that work. All you really have to do for these nonlinear differential equations, if you're trying to talk about stability, is look at the determinant and the trace. So for example, if we had, this is problem 15 from section 10.4. If our matrix, if our Jacobian was this matrix, 1 minus cosine of x2, sorry, where'd you go? x1 minus 1 times sine of x2, and then cosine of x1, negative sine of 1, that's a terrible number. And we want to find the stability, or we want to determine stability at the following equilibria. The first one is, of course, x1 hat, x2 hat equal to 0, 0. So we plug in 0, 0. Let's see what we get. Cosine of 0 is 1. So we get 0 there. 0 minus 1, sine of 0 is 0. Cosine of 0 is 1. sine of 1. Sine of 1 is a number. And all I know is that sine of 1 is positive. Because if you think about it, the angle 1 radian is in the first quadrant. You haven't gotten a full pi over 2, which is about 1.5. So this number here, negative sine of 1, is negative. Okay, this is going to be kind of unsatisfying. What's the determinant of this matrix? Right. What's the trace of this matrix? Negative whatever sine of 1 is. And in this case, it's actually inconclusive. If you look back at our conditions, it says to be stable, you have to have a positive determinant and a negative trace. To be unstable, you either have to have a negative determinant or a positive trace or both. But since the determinant is 0, you can't have any of those things happen, right? Being 0 means it's not positive and it's not negative. So a 0 determinant usually means it's inconclusive. Also, if you were to think about what the eigenvalues were, you'd have one negative eigenvalue and one 0 eigenvalue. And the 0 eigenvalue is kind of that weird case where you have all these different points of stability on the eigenline, but it's not your normal situation. So, yeah. On the other hand, if we look at this other more interesting point, like x1 and x2 both being 1, 1, well, then the Jacobian there is going to be, let's see, 1 minus cosine of 1. Okay, that's lovely. I'll have to think about that. 1 minus 1 is 0. Cosine of 1, negative sine of 1. Wow, who picked these numbers? The book did, not me. I have no idea if that's determinants positive or negative. Or if it's, well, let's see. So, good question. So, I mean, you could also just say what your eigenvalues are right here. And that's probably what I would do normally. But you could say the determinant is 1 minus cosine of 1 times negative sine of 1. We can actually figure this out. Is this positive or negative? Well, sine of 1 is positive, right? So if you think about the unit circle for a second, there's pi over 2 radians, which is about 1.5 radians. And there's about 1 radian. Literally, the radius is the same as the arc length you've got. Whatever that value is, sine of 1 radian is in the 1 radian is in the first quadrant. So sine of 1 is positive. So negative sine of 1 is definitely a negative number. 1 minus cosine of 1. Well, I don't know what cosine of 1 is either. I know it's positive, and I know it's less than 1. And you do too. Right? If you think about the graph of sine or cosine is always between what two numbers? Right. It's between negative 1 and 1. It can never go higher than 1. It can never go lower than negative 1. But cosine of 1 definitely is not equal to 1. Cosine of 0 degrees is equal to 1. And the next angle where cosine is equal to 1 again is 2 pi. I should say radians. 0 radians or 2 pi radians. So this is definitely less than 1. So we have a number 1 minus a number less than 1. This is going to be positive. And a positive times a negative is negative. So here, the determinant being negative means it's, I don't actually want to say the words it's a saddle. Because while locally it's a saddle, it's more just appropriate to say that it's unstable there. So I would say it is unstable at x1 hat, x2 hat equal to 1, 1. And I'll just for context, right? In questions 13 through 18 in the section, they don't ask you to say if it's a saddle or node or whatever. They just say, tell me if it's locally stable, locally unstable, or if you can't tell. So let's look at, let's look at 20 as well. If the term, yes, if the term, well, according to, so for nonlinear, you can't really say. For for a regular linear system, well, for a regular system, you probably wouldn't get the trace being 0. And the term. Now I'm curious. I guess for the trace to be 0. No, so what was your question again? Uh-huh.
That one was that you couldn't,
So the determinant was 0 and the trace was negative.
yeah, and that was,
And according to this section, we can't tell. It's inconclusive because the determinant is 0.
and that's always gonna happen whenever the determinant's 0.
I think so. At least like reading this theorem here. That's certainly what it says, right? Now I'm like a little more curious. Yeah, so if you look at either theorem 14 or theorem 16 in this section, theorem 14 says basically if both your eigenvalues are negative or their real parts are negative, then you get local stability. And if both their parts are, yeah. And if at least one of them is positive, then you get instability. And if one of them is 0, you get inconclusive. So if you're getting a 0 eigenvalue. So maybe what I said there wasn't entirely 100% true. Yeah, I guess theorem 16 doesn't say anything about that. Okay. So now I'm curious even more. Because now I feel like if the trace is negative, even though the determinant is 0, the trace being negative. Let's look at the answers. 10.4 number 15. I wonder what they have to say about this. Not that the answers are always correct, right? Sometimes there's mistakes, but it's still a good place to look. Maybe 10.4 number 15. Nope, they say it's inconclusive. Okay, good. And they do say the second one is unstable. Okay. Yeah. Oh, and okay, so yeah, that actually does. Yeah, that corresponds with what theorem 14 says, because theorem 14 says, let R be the largest eigenvalue or the largest real part of the eigenvalue. So in this problem here, we had a 0 and a -1. So the largest eigenvalue is 0, right? And it says if the largest eigenvalue is 0, then the analysis is inconclusive. So yeah, it could actually be stable around there, but this particular analysis is inconclusive. So that's what I would go with. Most of the time, you can just look at the eigenvalues, right? You don't have to do this determinant trace thing, but you can. So let's look at one more of these. Let's look at number 20, which has some really fun letters. So we have p hat equal to p times 1 minus p minus q. And we have q hat equal to q times 2 minus 3p minus q. And we're being asked to find the equilibria, find all equilibria, and once again, determine stability. All right, so as is typical, we can see that 0, 0 is going to do it. I should say 0, 0 is not always an equilibrium, but it almost always is, at least in the problems we're given. So 0, 0, we can definitely see. And then if q equals 0, we could also have, well, so then q prime will be equal to 0, but then we still need p prime to be 0. So if q equals 0, I'm going to set this part equal to 0. But then q being 0 gives me that p has to be 1. So another one is 1, 0. And then let's do the reverse. If we set P equal to 0, then we're going to need this equation to be 0. Since we already did Q equal to 0, now we're going to do the other factor. 2 minus 3P minus Q equal to 0. The P part's going to be 0, so we're going to get Q equal to 2. So we also have the point 0, 2. And finally, the hard one, right? There's always the one, so it's always very easy to do 0, 0, setting this part and this part with the 0. And then this one and that one 0, and this one and that one 0 are both pretty not too bad. And then these two equal to 0 require a little more work. So we're going to have 1 minus P minus Q equal to 0, and 2 minus 3P minus Q equal to 0. In this case, I might just subtract the equations together. Right? We can do this thing that we used to do back in other classes. We're like, oh yeah, I'm going to do this equation minus that equation, because I can see that the Q's will cancel out. 1 minus 2 is negative 1. Negative P minus minus 3P is positive 2P. And negative Q minus negative Q is 0Q equal to 0 minus 0. So then I have 2P equal to 1. So P is equal to 1/2. And then I can figure out what Q is going to be by putting it back in. So if P is 1/2, I have 1 minus 1/2 minus Q equals 0. So 1 minus 1/2 equals Q. So Q equals 1/2 as well. So that's my third point. Sorry, my fourth point. So that's my 4 equilibria, and then we have to find the Jacobian and then stuff each of those into the Jacobian to see what the analysis is. When I find the Jacobian, I really don't want to use the product rule. I'm going to definitely multiply these out. So I'm going to say that F1 is P hat is P minus P squared minus P times Q. And F2, which is Q hat, Q prime, sorry, I said hat before, is 2Q minus 3PQ minus Q squared. So then my Jacobian is, I really don't like writing all the things. I want to say, I know the first row is the F1, the second row is the F2. The first column is the derivative with respect to the first variable, which is P. And the second column is the derivative of the second variable with respect to the second variable, which is Q. So then the derivative of this with respect to P is 1 minus 2P minus Q. With respect to Q is minus P. The derivative of this one with respect to P is negative 3Q. And then with respect to Q is 2 minus 3P minus 2Q. And then we plug in all the points. So let's see what happens when we plug in 0, 0. We're going to get 1, 0, 0, 2. Two ways you can tell. One way you can tell what's happening is that both eigenvalues are positive. They're 1 and 2. That feels like the easiest way. The other way you can tell is the determinant is 2, the trace is positive, and when the determinant and the trace are positive, it's unstable. So either way you want to see this, it's unstable. I'm not saying it's an unstable node. I'm just saying it's unstable. I probably would have in the past said it was an unstable node because I didn't look at this section so carefully. Let's look at the next one, J of 1, 0. So now, if I were doing this on a test, I would probably give a little more information. I would probably say it's unstable. I would probably write lambda 1 and lambda 2 are both greater than 0. Or I would say the determinant is positive and the trace is positive. But I would give a little more substance so that the person grading my work knew that I knew what I was doing. And then if I plug in 1, 0, I'm going to get 1 minus 2 minus 0, so negative 1, 0. Oh, P is the first variable. I don't get 0 there, I get 1. Why don't they just use X? Make it confusing. And then negative 3Q is going to be 0. And then 2 minus 3 is negative 1 minus 0. So this one's going to be stable. My eigenvalues are both negative. Or my determinant is 1 minus 0, which is positive. And my trace is negative 1 plus negative 1, which is negative 2. All right, the next one, I think it was 0.3. No, 0.2, sorry. So plug in 0.2, we're going to get 1 minus 0 minus 2, negative 0. I keep wanting that to be the second variable instead of the first variable. And then plugging in q equal to negative 6, and then 0 for p and 2 for q, 2 minus 0 minus 4. Again, this is stable for the same reasons. Just like that one, both eigenvalues are negative. And finally, if we plug in 1/2, 1/2, we're going to get 1 minus 1 minus 1/2 minus 1/2 minus 3/2. 2 minus 1 is 1 minus 3/2 is negative 1/2. Oh, this one we actually have to work for. So this is an excellent example of where using that theorem is probably the easier way to go. Right? I could find the eigenvalues. That's going to be a little more work this time. Or I could say my determinant is negative 1/2 times negative 1/2 minus negative 1/2 times negative 3/2. And it looks like that's going to be negative because I have a 1/4 minus a 3/4, which is definitely negative 1/2. Unstable. The trace is negative, but it's unstable because it's in the saddle area of that picture. Again, I wouldn't say it's a saddle. I would just say it's unstable. Okay. Let's talk about where we're going. So let's see, where do I want? Yeah. That example is fine. Let's look at this example over here. I'll just do the one from the book. Sorry for the repetition from earlier, but I think that example from the book was a really good one. So I'm gonna do that one. So what we're going to do in section 7.6 is we're going to do some graphing of the phase plane and draw on these little direction arrows. So actually, let me grab one. I know we only have like 6 minutes, but I can say something meaningful in 6 minutes if I can find words. Always a challenge. It's amazing how things just like disappear from my field of vision. I had words I wanted. Oh, I know where they went. Just amazes me that I just misplace things. Okay, anyway. Oh, aha. Right, I covered it with another piece of paper that I was going to do something. Okay. Let's see here. Yeah. So here's what we're going to be doing. We want to, for a linear or nonlinear, for a system of differential equations, we want to be able to do is graph the null clients, identify equilibria, and then we want to indicate direction of motion, which I know is not particularly specific, but you'll see what I mean. So let's look at this example from the textbook, or not example, this problem from section 7.6, which is system of differential equations. This is problem 7.6, number 7. So here's our system. We have dx dt equal to x times 3 minus x minus y. We have dy dt equal to y times 2 minus x minus y. And let me ask real quick. Can you kind of tell that that's red? No? What a bummer. Well, you'll be able to see it when I post the notes later. I mean, yeah, I'd like to lie to myself and say I can tell them that's red because I know that I drew red there. But no, it's really like, you can see the color over here. Maybe there's a setting I'm not using. I don't know. I'll have to explore later, I guess. Okay, well, that's bonkers. Who decided that was a good idea? Okay, never mind. Play with it later. So we want to graph the null lines first. And the way to find the null lines is just by setting each equation equal to 0. So I'm going to set this equation equal to 0. Sorry. X times 3 minus x minus y equal to 0. And we're going to get two things. We're going to get x equal to 0. And we're going to get 3 minus x minus y equal to 0. Since I'm going to graph this, I'm going to solve for y. So that's going to be y equal to 3 minus x. And these are my x null lines. Which means on these lines, dx dt is equal to 0. So there's no horizontal change. There's no change in x. And then I will pretend like I'm doing this in red. I'm not pretending. So then for the other ones, y times 2 minus x minus y equal to 0 is going to lead to y equal to 0, or 2 minus x minus y equal to 0. Oh, sorry. That's even worse. Okay, you can kind of tell those are different colors, right? A little bit, maybe. Okay. So then we're going to get this one being y equal to 2 minus x. And again, these are y null lines, which means that dy dt is equal to 0. So now we're going to graph. And I do really, really encourage you to, if you have different colored pens or pencils, graph the different null lines in different colors. And also graph the axes in some other third color. So I would graph the axes in black and the y null lines in red and the x null lines in green or something like that. Here, since both of my axes are a null line, I'm just going to use one of the colors. So I'm going to graph the x null lines in black. So x equals 0 is the y-axis. So here's one of my x null lines. And y equal to 0 is the x-axis. So here's one of my y null lines. So this is dy dt equal to 0. This is dx dt. 0. Then I also have null lines along y equals 3 minus x and y equals 2 minus x. So 1, 2, 3. So here's my x null line. And here's my y null line, which actually is parallel to it. So also in red here, dy dt equals 0. Black here, dx dt equals 0. Okay. And we can see our equilibria right away. Wherever the black lines cross the red lines, that's where we have an equilibrium. So there's definitely an equilibrium here, here, and here. So there's definitely an equilibria at 0, 0, 3, 0, and 0, 2. Cool. Okay, so the thing you're going to do next, I know it's 2 o'clock, is you're essentially going to pick a point that's not on one of the null lines. So pick something like 1, 1. So I pick x equal to 1 and y equal to 1. At 1, 1, dx dt is 1 times 3 minus 1 minus 1, which is 1 times 1, which is 1. And dy dt is, 1, 1 might have been a bad choice. 1, 1's on one of the lines. Well, shoot. Let's see what happens when we get that then. Dy dt is 1 times 2 minus 1 minus 1, which is 0. So here's what we know is happening at the point 1, 1, which is right here. We're traveling purely in what direction? Left, right, up, or down? Right, right, because dx dt, which is the change in x, is positive. So we're traveling to the right. So the arrow there is going to be going to the right. What I actually wanted to show you was that if you pick a point not on a null line, like say over here at 3, 3 up here, dx dt is going to be 3 times 3 minus 3 minus 3, which is 3 times negative 3, which is negative 9. And dy dt is going to be 3 times 2 minus 3 minus 3, which is 3 times negative 4, which is negative 12. And so I'm going left, left and down. So at this point here, I'm going left and I'm going slightly more down than I'm going up. So I'm kind of going this way. And now here's what's true. Anywhere before I cross a null line, I'm always going that way. So in this section here, I'm always going down and to the left. And maybe it kind of varies depending on where I am, but I'm always down to the left over here. And then when I start crossing null lines, things change. On this null line here, dx dt is 0, meaning my arrow is perfectly vertical, right? I can't be going left or right if dx dt is 0. So over here on this null line, things are perfectly vertical. And then when I cross it to the other side, things are now moving still downward, but now they're moving to the right. Because I was going left, then I'm not going left or right, and then I change directions and I'm going right. So I'm out of time, I should stop talking. What I'll say is that whenever you cross an x null line, you change the x direction. I was going left over here, now I'm going right over here. Whenever you cross a y null line, you change the y direction. So if I crossed from this section here to this section here, I wouldn't be going down and to the right, I'd be going up and to the right in this little area here. We'll talk more about this on Wednesday when we have time, but I'll just leave you with every time you cross a null line, you're going to change the direction for that variable. Okay.